can learn from neutron stars if we can see them oscillate. That's basically what I mean by seismology, as opposed to seismic, which is motion in the crust. So, even though they sound similar, they're slightly different. So it's based on work I've done with the Kostas Klampedakis and Samuelsson. The Klampedakis was also in Southampton until a few days ago. Now it's in Sissa, in Trieste. So what I'm going to talk about is first I'm going to give a brief introduction to neutron stars, so we know what we're talking about. Some of these neutron stars are believed to have very high magnetic field. So those are, we envisage these as being described by something called a magnetar model. So I will talk a little bit about the observations of these. They tend to burst out in what's called flares, in X-rays and gammas. So then I'm going to talk about a little bit about the particular class of these neutron stars, which we observe as soft gamma ray repeaters, or SGRs. I'm going to tell you what these flares could be, and in particular, in the data from these flares, some of them, we see oscillations very recently, 2005. So these are the first time we've seen a neutron star oscillate, possibly, if our interpretation is correct. So I will try to present a model for what these oscillations might be. I'm going to give you two extremely simple models. It's basically toy models that will tell us about the physics, hopefully. So the first one is aimed to explain the origin of these oscillations, so we call it quasi-periodic, because they're periodic but not. It's like if you have a modulated sine wave, it will look when you take the Fourier spectrum. So you'll have peaks which don't belong to the oscillations, but belong to the evolution, rather. The second model will be aimed at trying to interpret the frequencies. We're going to try to learn, to see what we can learn about the neutron star properties from these frequencies. This is what I call seismology. So the subtitle could be this: what can we learn if at least few of the observed QPOs, quasi-periodic oscillations, are connected to torsional modes in the crust, which is what we believe they are. So this is a picture of a neutron star. So if you ever go to a neutron star meeting, you will see this about 100 times from Donald Park. So the basic properties of a neutron star is that it's formed in supernova core collapse. It's basically the iron core of a main sequence star, roughly say 10 solar masses. In the supernova, then, this iron core collapses and forms this neutron star. The rest of the star is ejected in the supernova explosion. We believe that the radius is roughly 10 kilometers or so from theoretical modeling and some measurements, but the error bars of those are huge. So it would be very nice if we can actually do something about the radius from other means, such as these oscillations. So the magnetic field in these objects could be very large. So here, the lower end is like 10 to the 8 Gauss. Compare that to the magnetic field here, which is about half Gauss, roughly. Magnetars, on the other hand, they're much larger, go up to 10 to the 16 Gauss. And that's close to the limit in nature. Because if you have a magnetic field somewhere around 10 to the 18 Gauss or so, the vacuum will become unstable to pair production. So it's a quantum limit on magnetic fields. And these are close. The periods, the rotation period, could be extremely fast. The world record right now is about 1.4 milliseconds. So it spins one lap in 1.4 milliseconds. So the surface particles are moving close to the speed of light, actually. And those usually have lower magnetic field and are usually seen as something called pulsars. And the reason why they have, the reason they can have such a low period of fast rotation is because they have a low magnetic field. low in neutron star terms. Because if you have a magnetic field which is mainly dipolar, say, and its magnetic axis is misaligned with the rotation axis, you will have a beaming of particles along the magnetic field, and that will break the star. The magnetars, which I will talk about, with these huge magnetic fields, they are slowly spinning, so around 10 seconds. Well, slow for these objects. The temperatures very rapidly after the supernova drops to roughly 10 to the 7 or lower Kelvin. And this is extremely cold. It doesn't sound very cold, but if you compare with the Fermi temperature of these matter at these densities, it's way below that. So in principle we can model them as zero temperature from many respects. So the structure then, we go from the surface, which I don't know very much about, the atmosphere. The atmosphere roughly will depend a lot on where it is. If it's in a binary system, you can accrete matter from a companion star, and then it would be mainly helium and hydrogen. If it isn't, you can have anything. It could be iron in a gaseous form. It's very, very thin, this atmosphere, millimeters or below. And then in the envelope, depending a little bit on the temperature, which on the surface, which could also depend on the environment, you can have an ocean of molten iron, basically. What I'm most interested in is the crust, which is this bluish region. It's roughly a tenth of it stands roughly a tenth of the radius of the star, so it's about 1 kilometer thick. In the outer crust, it looks like an ordinary solid. At the top it's iron. As you go down, the pressure increases, so the electrons get squashed. It's basically supported by degenerate electron pressure. As you squash the electrons even further, they come very close to the nucleus, and they can interact with the protons. So in inverse beta decay. So you get a neutron from a proton and an electron, and a neutrino, of course. So the nuclei becomes very neutron-rich. Pretty soon they become too neutron-rich to be stable here on Earth, but in these pressures they're stable. So we believe that these form basically BCC lattices, so normal solids. As you go even further, the neutron number will increase steadily. You will reach ridiculous neutron fractions. And also you can see up here, this is a cross section in the crust. As you compress, the nuclei will become closer and closer, and soon they're almost touching. And then you get topological defects forming. So first they become ovals, and then they form spaghetti-like cylinders. So you don't have a normal lattice anymore. Rather, it's a two-dimensional structure with strands of nuclear matter, and around it you have normal electrons and a gas of neutrons. As you compress it even further, it becomes looking like lasagna. This is why we call it pasta faces. So you will have plates of nucleons, and then you have gas in between. And as you go even further, this process inverts. So now,
do these spaghettis have a special orientation?
So, very briefly mentioned that, we don't know. So all these considerations come from microscopic calculations, which are pretty crude. That's one of the problems we have. So there is a guy in Oxford, Will Newton, working on this with solving the Schrödinger equation for, 5,000 nucleons in a box with proper block boundary conditions, trying to work out actually some more global properties. I think Nikolai Chamel is also working on, he's in Warsaw now, I think, working with Paul Hansen. But we don't know. This is actually crucial. That's what I'm going to say later on, because if these actually form very long oriented strands, you will have something which is highly anisotropic. Whereas if they form small strands which are randomly oriented, you will have something which on a large scale looks isotropic. But we don't know. Anyway, as you go even further, then you come into homogeneous matter, and then it turns into fluid. It's no longer doesn't have any solid properties. So this is the outer core. This we basically know how to model. It's just neutrons, protons, electrons, and some muons forming fluid. The neutrons will be superfluid, probably. You might get superconductors and so on. But basically we know the basic properties here. And this describes our knowledge of the core. We don't know anything, roughly. Could be whatever you like, depending on which theory you prescribe to. Could be free quarks flowing there. Could be hyperons. Could have meson condensates, like pion condensate, kaon condensate. And we don't know. So this is what we want to know of these stars. It will tell us about the strong interaction. So this data from, if we know the structure of the star, we can say something about the strong interaction. So the key questions we have: what is the equation of state? So what is the relation between the pressure and density, say? So what is the magnetic field configuration? It would be interesting to know. And then I told you briefly that there's superfluid and superconducting possibly. So how do we describe those? What's the parameters we need to describe them? We have theoretical models for all these, but the parameter estimates are at best order of magnitude correct. Probably not even order of magnitude. So we know that seismology has been used. It's been used here on Earth, for instance, to tell us about the structure of the Earth. Used on the Sun very successfully. We have thousands of modes observed in the Sun. So we know properties of the inside of the Sun. Of course, the problem is we always see the surface. We want to know what goes on inside. And basically what I would call seismology is this. If you have the structure, so if you know all these key points, you can work out the set of oscillations that are allowed in the star. If you work this out, it's unique and you find them. So you have a structure to mode relation. What we want to do is take the modes and see what we can say about the structure. Obviously we will never observe all the modes, so there will always be a lack of information. But it's interesting to see what we can say if we measure oscillations. I would mainly be interested in mass and radius, because that would constrain the strong force, at least slightly.
Sorry, so now you're talking about single star or the standard binary system, or it doesn't matter?
I would be talking about magnetars now, so they are always observed as single star. But in general, for seismology, we can look at any system. But we don't have any oscillations. We're eagerly awaiting the gravitational wave detectors. So, the magnetars then, they seem to flare. So they burst out in X-ray and gamma rays. And Duncan suggested a model for this in '98, which is the prevailing theoretical model, I would say. It's sort of hand-wavy, but it goes something like this. In the formation of the star, you have a highly magnetized main sequence star. It collapses and then forms a supernova. It's also rotating, and it's quite warm, of course, to start with. So you get convective modes, and you get the dynamo building up a twisted magnetic field. Then the star cools. The magnetic field is highly twisted inside, and it wants to unwind to lower its energy. That would, since it's cool, you have the crust. It will stress the crust. It can't move past the crust, so the crust will get stressed. Eventually it breaks somewhere. It sends off these seismic waves. Since it's already pre-stressed everywhere, it would crack everywhere basically. So you would have tectonic plates, if you take an analogy with the Earth. And then, since it can move now, the magnetic field will reconfigure, try to find lower energy. And that's what we observed, and the magnetic field lines are wobbling wildly, trying to reconfigure itself, and interact with the surrounding, sending out various radiation.
But the stresses would also work in the interior, no? Both in the interior and the crust.
Well, there's no stress in fluid.
In the interior.
Yeah.
Magnetic stresses, you mean?
The magnetic stress, yeah, but there's no elastic stresses because it's not elastic.
Uh-huh.
So there the fluid can move.
And respond to that.
It's basically perfect MHD.
Yeah. Okay, thanks.
So some artist at NASA has done this movie of it, and we're going to see this magnetar picture here. It's a star, we have a magnetic field going out. You're going to see, if you look closely, how the crust cracks, and then you get the bright flash. In the end, you will have hot regions at the poles. You see those. This is where the radiation comes from. This is consistent with the model and the observation, because you see these oscillations that I will talk about later. They are seen at certain rotational phases. So those will be seen when the hotspot is pointing towards us. Let's see how it looks. This is just, of course, a cartoon. So there it cracks, you get the bright flash, and it settles down. And this is the tail part that I will talk about, where you see these bright flashes at the poles, magnetic poles. So these stars flare all the time. Occasionally flare giant flares, which are extremely powerful, and this is how it looks from Earth. Well, in this picture, in gamma rays, if you could see those. And here comes a shock wave or something. No, it's not shock wave, it's just a wave of electromagnetic radiation. It hits the magnetosphere of the Earth, and it actually turns on to daytime activity. The brightest one was seen 2 years ago, almost precisely. And it was the brightest thing we've seen for a long time. It's 1,000 times brighter than the entire luminosity of the galaxy. It's like it's supernova, basically, they can compare it. Yeah, so.
Is this periodic?
Sorry?
Are the flares periodic?
No, they're actually they're randomly distributed according to a law which I don't remember, but it's the same law that governs earthquakes. It's the same statistical property. So they come in bunches, basically. And you usually observe small flares after the first one. It's like aftershocks. So that's why we believe the theory is pretty good. So these flares and substrate gamma repeaters, SDRs. SDRs are observed as persistent X-ray sources. We see them in X-rays all the time. And then occasionally they flare. So the model puts them around 10 to the 15 Gauss. It's consistent with the spin down, so you measure how fast they're spinning down. And that would be, if we assume that the magnetic is mainly a dipole, that would give you the magnetic field strength. Its period is around 1 to 10 seconds. And compared to other neutron stars, such as pulsars, for instance, they are quite different, because they're slowly rotating in high magnetic fields. The energy stored in the magnetic field is much larger than the kinetic energy stored in rotation. So these flares cannot be due to some rotational instabilities or anything like that. It has to be related to the magnetic field. We've seen 3 giant flares since we had X-ray satellites. The one in 79, I will not talk much about that because the instrumentation wasn't good enough. I might have seen one of these oscillations in that, but well, there's no statistical significance of it. We have one in 98. I'll just show you the data for that later on, but I will not talk about it because the data is not as interesting as the one we got as a Christmas present 2 years ago, which was the most energetic we've seen. So as I said, they are associated with large-scale magnetic activity and cross-sector. The interesting part for me is that in the tail, you see these periodic oscillations. So this is the data from Strohmeyer and Watts. And it's a power spectrum. So you have power here and you have frequency here. It's basically Fourier transform. And you see these peaks. This is in the tail. It's not in the peak because the peak can't be resolved. It's very narrow. It's only a fraction of a millisecond long, and it saturates all the instruments. In fact, they actually saw the reflection of the moon. And that could barely be resolved. So you see these peaks in this power spectrum. These are the oscillations that I will talk to you about.
So two frequencies, you see, or how?
I will tell you, these are the frequencies we're
Oh, I
seeing.
see. Mhm.
So if we start with this one, which I'm not going to talk about anymore later on, you see these 4 peaks. There are suggestions of other, but these are the significant ones, the ones that you can actually make a claim that you've seen. So these are what I would call in the low range, so it's 30 basically to 150 hertz. In the other one, in this 1806 minus 20, it just gives you the position basically. You have some in this low range, and you can see they're looking slightly like this. You have some lower ones, and you have also in the kilohertz range. So yes, if we think about it as an oscillation in the crust, could be one of the possibilities. You can just make a very simple argument to look at standing waves in an elastic crust. So very simply, so the frequency of the fundamental nodes are the ones who doesn't have any radial nodes. So it's basically the whole crust moving as one peak, like that. You have this is just the time it takes, the inverse time it takes for the wave to go around. And then you have the number of nodes in the angular direction. So the L here is just the angular quantum number from the spherical harmonic YLMs. So it's just the number of nodes in theta in the phi direction, depending on how you interact it. So this is the shear velocity, and this is the radius of the star. So if you look at the lower ones, and you just adjust your velocity to explain this is 29 hertz, I will explain why I just choose that one. You can see that for given out here, you get frequencies roughly equal. So using the same velocity and looking at standing waves in the radial direction, which would be the overtones, so this is oscillations going radially, you just get standing wave criterion there as well. With the same velocity, it doesn't really give you the correct numbers. I could put 2 here and get 744. That wouldn't be very good either. We're not too worried about that. Because here we've modeled this as being constant. But this is an oscillation going radial, so it would depend on the structure in the crust more than an oscillation just twisting the whole thing. That would depend more on the average properties, whereas this will depend on the detailed properties. So we're not too worried about these. We can sort of accept that for now. The lower ones, for reasonable neutron star parameters, they cannot be really explained. The 18 hertz cannot be explained. So this is a worry for this model. Oh, by the way, I should have said that delta is the crust thickness. So it's about 10% of the radius, of the thickness of the crust.
What about the L equals 3 for some of the intermediate ones?
Sorry?
They're missing. I mean, L equals
Yes.
3 to 6, for example.
Yes, so we want to explain why certain, this is one of the things we want to explain. Why are certain ones cited? If I have to guess, I would guess it depends on the geometry of the magnetic field. So you have a spherical star, and you have a geometry of magnetic field which is different. So that doesn't decompose in YLMs as easy as the spherical things. So, but we don't know why, and you shouldn't take these too seriously either. This precise number, I will show you later. Better one.
What's the V perpendicular?
It's the shear velocity.
And how large is it?
It's at the bottom of the crust is roughly 2 times 10 to the 8 centimeters per second. So it's
Fast.
1% of the speed of light.
Is there a theory for that? For the beam probe?
Yes.
So you can actually trust that?
Yeah.
You can actually use that value?
Yeah.
Predictions.
Yeah. So, but then we have a more serious problem, because these are pure elastic waves going. But we have a huge magnetic field. So you can, that magnetic field, unless you have a type 1 superconductor in the center, in which case the magnetic field will be expelled, that wouldn't be a problem for us, because then we would have to have corrected magnetoelastic waves in the crust, and that would still give us the right order of magnitude. So if you exclude that case, you will have magnetic field penetrating the core as well. So if you just roughly work out the time scale it takes for Alfvén wave to go through the entire star, it takes about 70 milliseconds, and that's about one oscillation period. So in basically less than a period of oscillation in this elastic crust, the whole star will know about it through these magnetic interactions. So the whole star will wobble. So there are no crust waves. I mean, mathematically they don't exist. You have to work out the global MHD modes of this star. So the puzzle is, why do we observe the seismic frequencies? There is a whole forest of these modes. And they can have any frequency from however low you want almost to as high as you want. So this is a sort of a puzzle. And that's why we made a very, very simple toy problem. It's a plane parallel star. It looks like this. You take the spherical star and you split it and you open it up and make it plane. So it's a reasonable assumption in the crust, because it's a thin crust. Whereas in the core, of course, it's complete bogus. But just to see the physics of this problem, we make it as simple as you can possibly do. You make it constant density, constant shear modulus, which means constant shear velocity. We assume perfect MHD, ideal MHD, so there's infinite conductivity. But what we do, which is new, hasn't been done before, we take the correct boundary conditions. Most people put the oscillations to 0 at the cross core. But if you work out force balance, you see that this displacement vector shown here, which we assume is in this direction, is actually continuous across the boundaries. And then you get this global modes. So what you do is just technically solve the Euler equations. You assume some mode kind of solutions that's proportional to the exponent of I omega t, with omega is the angular frequency. And you get this simple equation in the end. It's constant. All these coefficients are constant, so it's just a trivial equation to solve. First year undergraduate. So before I tell you about the spectrum of that, let me tell you about what people have done before, and and it will emerge why I do that later on. So if you take the artificial boundary conditions, you set the oscillation to 0 at the surface of the core in the boundary. You can work at the frequencies in the crust only, because they don't depend on the core now, and they become something like this. Here we have the Alfvén velocity, so this is the velocity of magnetic waves, basically. This is again the shear velocity. The n is the number of radial nodes, r is the radius of the star, which now is more like the z direction. Delta is the crust thickness. L is again an angular quantum number, if you want to call it that. So if we see for the fundamental nodes, no magnetic field comes in. This is entirely due to our simple geometry. Roughly speaking, since these modes are tangentially moving, they're moving perpendicular to the magnetic field. They're not affected by the magnetic field. If we had an inclination of the magnetic field, they would have a component along, and then that would basically boost the shear modulus and will affect our frequencies. We see this here in the radially moving ones, which has non-zero n. This is basically a boosting factor, depending. So you get this faster velocity. You add the squares and take the square root of the shear velocity and the Alfvén velocity. So these were the crustal frequencies. In the core, we have pure Alfvén frequencies, so magnetic. It's not magnetosonic waves; it's magnetic shear waves, or I don't know what's called. Alfvén waves, looking like that. So if we turn to the correct modes, we have a very dense mode spectrum. It's plotted here in black lines. But these are the correct modes. I can't give you an explicit expression because when you solve the boundary conditions, it's not exactly solvable. So you have to do it numerically. It's a very simple task to do. So the black lines are the real ones. The dashed lines here are the core rain waves. This straight line is the crust mode. And this is where L equals 2, N equals 0. So it's a mode going like this with no radial nodes. And what we see is that all these lines cross. And they only cross. There's always triple coincidence. You can actually prove this mathematically. It will always be like this. So what we have here is a resonance, in a sense that I will define.
But I mean, the crossing of the dashed and solid lines, that's of no physical significance. That's just
No, neither the green line or the dashed lines have any physical significance. Nevertheless, mathematically, they cross there. Surely it's not a coincidence. So what we do, if we take the correct modes, we work out the total energy in the crust region, and we work out the total energy in the core region, and here we plot the ratio of those. We have the energy here in logarithmic scale, we have the mode frequency here in some normalized. You can put in units once we want to compare with neutron stars if we want, but for this toy it's not really having a scale. And what we see is that when the frequency, so let me go back again, when we have this one, for instance, this crossing, that mode is here. It has a much higher energy in the crust than in the core, or the ratio is much higher than compared to the other ones. So if you envisage the excitation process being the crust cracking, and then transmitting energy via Lorentz waves, then it's more likely that the ones who have more energy in the crust are excited. So it's more an excitation argument. There are lots of magnetic modes, but the ones that have frequencies close to the crustal frequencies are the ones that would be excited in the crust way. And you see, it doesn't depend on fine-tuning. So you can argue that, we chose this because it's very exactly at the resonance, therefore it works. Or you can choose something which is off. And you still get this peak here. It's not as evident, but there's still a peak. It's preferable to excite that mode. So what this tells you is that the frequencies that we will most likely observe are the ones that are close to the crust frequency. So this is consistent with the data. Additionally, if you look at this, you see that these are a bit higher. So on the low side of the excited frequency, there's a bit more energy in the crust than in the core. There's about 3 of those. You go back and you plot those dots. Okay, well, if you plot actually the measured ones, which are the 30 or so, 26 and 18, they wind up on that line. In addition, you can see here, if you just draw a line straight here, you will have another one there. That will be on about 22 Hertz.
So all these different dots are for different values of n, right? And for a fixed value of n?
Different Alban modes. So whatever number you want to integrate.
But it would be the vertical wave number n, therefore.
Yes, right. For the Alban modes. It's a number of...
And L is fixed, or what? Is that right?
This is... Now I compare them to the n equals 0 crust mode. I can look at... This argument works for all crust modes. There will be resonance for all the crust modes.
Just to get it straight, I mean, what you're saying is that when the Alban mode is roughly equal to the crust mode, then of course you get a resonance.
Yeah, the problem is...
Essentially something like
that. Essentially, but the problem is that neither of those modes exist. You only have the global ones.
Yeah, okay.
That one. Anyway, if you put in these numbers, you get this set of frequencies, so you can explain the lower ones, and you actually get another one. So we talked to Anna Watts, who do these detection things, and you can't really say nowhere yes, because there's no statistical significance in it, but could be not, so we don't know. But it would be interesting if we had another giant flare and see if we could actually, if we get that structure again, it would be quite a strong argument.
But this was all for the SAT model. Would you not expect that the frequencies may be quite different for different geometries?
Of course.
Yeah.
So, I mean, I don't want to make any predictions from a flat plane, but the physical mechanism, the ones closer and lower, seems to be robust.
Yeah, right.
Obviously, we need to build the models spherical, and
Sure.
if you want to interpret the data, it has to be relativity as well. Anyway, so the conclusions here are basically that if we have this strong magnetic field, then we have global modes, but those modes that are easily excited by crossquake have frequencies close to the crust frequencies. So the argument is really that it's the crust frequencies, it's not elastic crust frequencies, it's the frequencies of the crust with a magnetic field inside it. But you can treat the crust alone. And the model also offers explanation for the low frequency modes. So to see what we can do seismologically, I'm going to do another toy. It's a different toy. It has no magnetic field. It's a relativistic model. So we have a sphere, it's cold. It doesn't have a magnetic field. It's spherically symmetric, it doesn't rotate. It's a perfect fluid core, perfect elastic crust. We do it in what's called the cowling approximation, so we ignore basically the coupling between gravitational waves and matter. What we do is we include a recent model of elastic material, which is more general than that we used before, so we can include anisotropic solids as maybe needed for these pasta phases. And it's also instructive, as I will show you.
That's related to your question, right?
Yes.
And you were saying you don't know much about the...
No, but it's I would say it's quite instructive if you think about it later on. The key point is that with this simple approximation, the crust is decoupled from the core completely. So you can just look at the crust. So given an equation of state of the crust only, which is easier to obtain because it's closer to normal properties of matter than the core, on which we don't know anything. So given that equation of state, we can work out the modes, and they will only depend on the mass and the radius of the core. So that's all, the two parameters, giving you all the information about that. We used a recent equation of state, and we take the shear modulus to be described by BCC lattice, which again, in the pasta phases is not very good, but we need to take what we have. Yeah.
This perfect fluid core, does that mean you don't sort of consider waves in the core, or
there won't be any because I don't have any viscosity, and these are waves going
like.
like.
It's a perfect fluid.
Yeah.
It's like a perfect fluid.
So it's because it's just torsional modes, so there's only velocity perturbations, so there's no friction. So yeah. So this is how the model looks. Very simple. It has some radius, some core radius, some crust thickness. It has two different shear velocities, one in the radial direction, one in the tangential direction. I always set units such that G is equal to C is equal to 1, so this is Newton constant, this is speed of light. I also define this parameter, which is mass over radius, which is now dimensionless because I have these units. It gives a single wave equation. I don't have to show that. And I computed numerically a lot of modes for a lot of models. But what I'm going to give you instead, for all this numerical data, is I'm going to show you a WKB analysis of the equations, because those are more instructive. So for the fundamental modes, now we have these again, no radial modes. It doesn't quite look like the one I showed you before. First of all, the dependence on L is different. Before it was LL plus 1, now it's this. When we check this, we get the numerical data, and it's ridiculously good, very surprisingly.
That's what
numerical precision, 10 to the minus 1.
Which values of L, roughly?
For any L that we try.
Any L?
that we tried. I computed the first 15 or something. So instead of scaling like, this is the square frequency, so instead of scaling like R squared, it scales like R and RC. So this is also sort of reasonable, because you take sort of the average property when you isolate it as a thin shell. So this is the geometric mean. You have a redshift factor, which we expected. And then interestingly, what comes in, as you would have expected, is tangential shear velocity.
Is that the same as your V perp earlier? Or is it?
Yes, but now I have two, so I have to distinguish them.
I see.
Yeah. So, but this tangential one comes in here. If you look at the overtones, we start with this complicated factor here. All you need to notice about this is the crust thickness divided by basically R, and that's squared. So delta is 1/10 of R, so this will be a factor of 1 over 100. So this will be always a very small correction unless L is very, very large. So you forget about that. It doesn't contain very much physics. Again, this looks precisely like the previous estimate, except for the redshift, of course. So it looks precisely the same.
So beta? Did you say that was redshift?
Yeah, it's M over R, so this would be the redshift factor.
Yes.
So in order to do seismology, we want to deduce the full radius and the full mass. So I made an estimate of how thick the crust is, depending on the compactness. A very simple estimate using polytropic equation states and so on. Approximating the gravitational field to be constant, the gravity is also pretty good, and so on. You wind up with an expression like this, where alpha is the parameter depending on your equation state. It turns out that it mainly depends on the pressure over density at the crust core boundary.
What is negative? Is 2 beta bigger than 1 or something?
Sorry?
I mean, delta should be equal 0.1 in the end, roughly.
Yeah, so beta is roughly 0.2.
0.1.
Alpha is a very small parameter.
But then alpha must be negative. No, I'm sorry, it's minus 1 then.
Yeah. Yeah. So alpha is small, so basically you can throw that away and invert this and take away that. The key point is that we get the frequency in this form. You have some velocity over some radius and then a function of compactness. So we try that against all the modes. Again, it's very accurate. We can get estimates of this form which are accurate to within fractions of descent, spanning a huge parameter range. So we have a very good analytic formula. And it's clear if we have a fundamental mode and an overtone, if we were to know the equation of state, we would know these velocities, then we can solve for R and M from these equations. So you have to see how it works. These are the frequencies of this soft-gamma ray repeater. So I added a few here in parentheses because they're not significant, but I put them in there. So I'm going to show you the mass radius diagram for neutron stars. I usually plot these to show how various equations of state give different results. So in this we have the mass in solar masses. I have the radius here. And these curves are just examples of computations of equations of state. So along these curves, each point corresponds to a particular star with a particular central density. If the density increases, you go along this side of the curve. So each point here corresponds to a particular star if that equation of state is correct. We want to know which one. You see they differ quite wildly here, so we want to know which one is correct. So if I start by identifying, led by our toy model, start by identifying the this 29 Hz feature with an L equals 2, N equals 0 mode. I can solve my equations for M and R, but they will be parameterized because I only have one frequency now, so I can't solve for 2. So I will get a line in this diagram. So if this model is correct, my equation of state is the correct one, and so on, then the star must be along this line. I can try this by testing these frequencies. They turn out to be at 6 and 10. You see they're slightly different from the toy model, toy calculation, Newtonian constant and so on. But now I exaggerated them, so they're very thick lines, otherwise you wouldn't see them, but they wind up on top there. So that seems good. They agree. Turning to this one, let's check if it could be an n equals 1 mode, for instance. And then, if it is, then you will wind up on that line. And this is very good news, because these lines, they cross. So you will have a very narrow region in this parameter space where the star can be, if the model is correct. So you have to show you the numerical, so then we find the mass here. It's 1 solar mass and 11.5 kilometers. This is slightly worrying because it's too light. It's hard to envisage in a supernova core collapse that you would have a star which is less than a solar mass. But the model is very simple, so I will tell you what we could do about this. Yeah.
In the very early slide, you said that the original mass of the supernova was 10 solar masses, if I remember. And then you said that the resulting mass of the neutron star was like 1.5 solar masses.
Yeah, it's roughly the Chandrasekhar mass.
From 0.96.
Yeah, it's 50% or so. Yeah, it's slightly worrying, but this is what we get from this simple model. There's a lot of uncertainties, and we'll go into this. These points that I put on here are from the numerical data. So here, yes, I computed a lot of models here, computed a lot of frequencies. I scanned the data for the ones that can explain these frequencies. And then I actually don't have to tweak anything to get this identification with the 29 Hz. Because otherwise, if I choose the 26, for instance, it wouldn't overlap. If you choose 18, you would wind up here, which is completely unreasonable. But we have a lot of uncertainties, of course. So what are they? If you have a magnetic field, which I ignored, I told you before that what basically happens is that you boost the velocity. And you will boost the velocity along the magnetic field line. So the main effect is that you get corrections of this kind. And this has actually been worked out in another model by a group in Thessaloniki, Sotani and Kostas Kokotas and Sergiolas. And they worked out the modes actually. And you find always that you have a correction of this form, where C depends on your equation of state, your magnetic field configurations, and so on. So I just taken that data and I sort of estimated how large this can be. We'll see the result of that later on. Then we had this fitting factor coming from thickness, so it depends on the equation of state of the crust. Just to see how much it differed, I took 3 examples. This was the one I used, Dushai and Hensel. There's an older one by Bain, Bethe and Petek from 71. And a third one, but these are basically the ones that exist now, by Negley and Watering. And I checked how my results depend on using different equations of state. And it turns out the main dependence is the pressure over the density at the interface. And this is quite an unknown parameter, unfortunately. It turns out that you have a variation of a factor 2.5 roughly in this parameter. Then we also have, possibly in the faster phases, we have a reduction of the shear moduli, according to Petek and Potemkin. So they claim that you can have a reduction of the shear modulus up to a factor of 2. So these are huge uncertainties. So we are eagerly awaiting these results of new calculations to see if we can construct this better. As you can see, these are pretty old, and this one was actually not done in order to improve our knowledge of the crust. This was more done to build a single theoretical model. Anyway, if we take this data, so first, I just see what happens with, I put a little box here, which is basically where my star should be. I take the magnetic field corrections with the uncertainties suggested by their results. Now they haven't included toroidal fields, So again, the box will grow. But you wind up here. This is even more worrying. You basically can't have stars here. If you have stars down here, and they are described by, all the neutron stars are described by the same equation of state, then the most rapidly stars would be unstable because they have very low mass and very high radius. So if they're spinning at 1.4 milliseconds, it would throw off the matter. So they couldn't exist. So this is very worrying. Now I add the uncertainty in the pressure and density, and you see, then the whole box goes up here. This is very good news. Of course, it's bad news for predictions, because now my region of allowed models is soon spreading the entire parameter space. But, as I said, these calculations are probably not the ones you should primarily trust. So it will be interesting to see these new calculations. Hopefully we'll wind up somewhere here, and then we're in business again. We also have the uncertainty in the shear velocities, Pethek and Potemkin. If you add that, you have a allowed region like this. This is not very impressive. The point here was very impressive. This is not very impressive. But in fact, this is better than anything we have before. Before there had only been crude lines saying, oh, GR excludes this region, and rotation includes that region, and everything else is allowed. And you would never see an observer have an uncertainty in the radius of order just 1 kilometer like that, plus minus 1 kilometer. And the good news as well is that the physics we need to add to improve this can be done, and it is being done at this moment. So I expect over the next 5 years or so, this box will shrink, and we'll actually have some data. So to conclude, some of these coarse periodic oscillations that we observed could be elastic MHD modes, which are tuned then to the crustal frequencies. And with an improved theoretical modeling, we could put constraints on the neutron star, and hence the equation state in the core, which is highly unknown. To do this, so what we're doing at this moment is to build a global magnetar model, so a model which envelopes all the pieces of physics that we know. So we can test our predictions of this mode excitation idea in the real setting, so on. We also need to improve the understanding of the inner crust. And this is being done by several groups. So these are very difficult problems. It's basically because there's no symmetry wherever. It's just a horrendous problem. But it's very important, because I think if we solve it, we can actually put constraints to the equation of states. We can have at least one dot in this mass radius diagram. That would cause quite a stir in the strong force community, I think. Right, so this is what we're working on right now. Thank you very much, and Merry Christmas.
Thank you very much. So, questions?